diagnosing cancer or delineating cancerous tissues from normal, right, using three different modalities: electrical, mechanical, and thermal. Today we will see three different applications of microchips or microsensors, or you can say a smart sensor, right? The reason of saying smart is because of its usefulness, the effectiveness in the environment, which have never been thought of in early cases. Now, to do that, let us start with the first topic, and that is on a steerable intubation catheter integrated with MEMS-based sensors for chronic upper airway management. Now, let me go word by word so you understand what is the title, and then we'll go into detail about the sensor. A steerable, that means you can steer it, right? Like you can drive the car, drive the bike, so you can steer the bike, so you can go in the direction that you want to drive the car. Same thing, steerable, the meaning remains same, only it is for the catheter. Catheter is a tube that can be placed within the human body, right, for either identifying the disease or for curing the disease. Okay, so that's a catheter. Intubation is within the body, so it's intubated. Integrated with MEMS. Integrated is like you can integrate, right? MEMS stands for micro electromechanical sensors for chronic upper airway management. Chronic is there is a difficulty, there is a disease, there is an inflammation. These are all chronic. Upper airway is the windpipe that we breathe in and breathe out. The upper airway is also called trachea. Okay. And then we have management. So what exactly the project is about? So you see the background here, and what you will see is that the chronic upper airway inflammation remains a diagnostic and therapeutic challenge for pediatric surgeons. Why we are talking about pediatric surgeons is because the infants who are on ventilators, certain times they develop this inflammation of trachea. On the right side, you can see a 3D volume rendered image of a 6-year-old boy with a history of long-term intubation, right, and tracheostomy placement. So you can see here the windpipe is narrowed down, right? It is there is a stenosis. Stenosis is a inflammation of the trachea. Okay. So studies have shown. So what is another background is that constriction in the small airway geometry requires an individualized approach with timely diagnosis. See, if you cannot diagnose this correctly, it will be difficulty for a person to breathe in and breathe out, right? And sometimes a person can get choked because he cannot, the patient cannot breathe. So the studies, that is, the literature shows that a subjective assessment, that is conventional bronchoscopy or CT scan images, is often based on suspicion index. Okay, it looks like, right, and has led to misclassification of airway narrowing. Sometimes airway may not be narrow, but it looks like it is narrowing. So this is like suspicion index. So if you see the statistics in particular, what you understand is that acute respiratory infections are a major cause of morbidity for mortality in young children, significant burden to child health both globally and in developing countries like ours. 85 to 88% of respiratory infection episodes occurs in young children are acute upper airway infections, claiming about 3.9 million deaths annually. About 1 million is about 7 crore, right? So or 10 lakh, right? So you can understand that this is a huge game. It's a huge burden that is there on the global health, and that's why it's very important to identify or diagnose the stenosis or the inflammation of the upper airway in earlier cases. Now, so the challenges remains is anomalies of upper airway. Second is there is a definitive diagnosis such as anomalies calls for a team of competent clinicians, sophisticated clinical settings, which becomes challenging in many countries. Okay, like I said, we have tertiary clinic with excellent facilities. When you go to secondary clinic, it has little bit less facilities. When you go to primary healthcare centers, it has a minimum of facilities. So this kind of competent clinicians and sophisticated clinical setting is very difficult to place all the way to primary healthcare centers, even in the secondary healthcare centers. So the second challenge is the variability in clinical symptoms, diversity of the associated anomalies, and scarcity of resources present significant challenges. Next is that if you use CT and there is a long scan times in both MRI and CT, then in CT high radiation exposure is a difficulty, and for MRI, those who know about how MRI works, right, it takes long time to identify the particular anomalies. Next is we require a patient cooperation providing inspiration and expiration images, right? That he has to breathe in, he has to breathe out. This lot of cooperation from the subject itself is required. Last thing is a child is incorrectly diagnosed with severe asthma when they really have tracheomyelitis. That means that it is not asthma, it is actually the narrowing of the windpipe. But because there is a narrow windpipe, the child cannot breathe, and the diagnosis comes as asthma, but it's not asthma, right? So there's a wrong diagnosis. This is the only reason why it is important that your child's physician has a lot of experience diagnosing and treating his condition. So if the clinician is expert, he or she can diagnose it correctly. Now, before we develop our own things, we should understand what is the current technology and why we require to develop our own things. Okay, so right now, if you see current technology, so evaluation and characterization of stenosis. Stenosis is a inflammation of the upper trachea, right? Is using endotracheal tubes like this. What you can see, right? They blow this one, and then we can see that what is the diameter of this, so that we can find it out what is the diameter of the trachea. The most widely used objective method for measuring stenosis in clinical practice, which is this endotracheal tubes, and needs interchanging of tubes multiple times to give crude estimation of the degree of stenosis. Next is the Kirshner wire measurement sticks, which was proposed by a research group in 2015. The measuring sticks needs to be swept until the right fit is determined. Many times you have to put it and then take it out, put it and take it out. The next one is measurement of tracheal stenosis with the rigid bronchoscope, like this, what you see, right? Optical distortion may lead to imprecise measurement. Finally, severity of narrowing often misclassified, right? But what is the severity of the narrowing? How much is narrowed? So quantification is very difficult using this technique. So what we are proposing, right? Or what is the need of R? There is no definitive surgical approach, right, to repair tracheal abnormalities. As a surgeon lacks a real-time estimation of the airway caliber, we require a valuable guide to pediatric surgical therapy. There's a need of developing or deployment of a tool in a clinical setting with improved assessment of disease. The last one is the multifunctional sensor integrated intubation catheter will be a first of its kind diagnostic tool that we are working on that can be used for monitoring infants and children with chronic airway obstruction. So if you see the objectives, right, because before you develop sensor, we should understand that what is application, and based on the application, what kind of system we are designing. Based on system we are designing, what kind of sensors we have to design. So it goes from the final objective and we have to come back to the main objective. So if you see, we see the subjective of objective 2 first, which is quantitative assessment of the non-linear elastic property of tracheal in tissue. That means that when you put or insert the catheter inside the trachea, right, you need to understand what is the diameter of the trachea, and you should also understand what is the elasticity of the tissue that you are measuring. So this both can be done by developing sensors. One can be microflow sensors, I'll tell you why. And second can be a force sensors that can be used to understand the elasticity of the tissue. And then we have to use it for excised sheep airway. So sheep trachea, we take it out. Of course, we don't kill the sheep. We go to the butcher shop. If we get the trachea, we bring it to the lab, we measure it, right, and we discard it as per the protocol. But to do that, right, we have to understand that tissue elasticity, the tissue compliance, and second is the force feedback, and third is the flow, that is diameter of the trachea. To do that, we have to design and fabricate MEMS-based flow sensors, integrate sensors with catheter, experiments both in situ flow patterns and in phantom models. Finally, we have to do validation in a excised sheep airway. So this is a 4-inch silicon wafer on the right side of the screen, right? And you can see that the left side shows the masks. It's a single mask process, very easy to fabricate, right? Those who understand fabrication, it's you have a thermal oxide, take a silicon wafer, grow oxide is SiO2, or perform and then deposit you can do a lift off here, so you can perform photolithography by spin coating photoresist. Then you do the metal deposition, dip this wafer in acetone. So the metal which is here, where my arrow is pointing out, will stay and the photoresist will be etched, and so you can get this micro heater patterns as you can see on the SCM image on the left side. And these are nothing but a temperature sensor, because some metal, if I apply a heat, right, it will show change in resistance. If I apply a voltage, it will increase the current, and because of flow of current, there is a generation of temperature. So that means that this same structure can be used as a heater and can also be used as a thermistor. Now, what is the idea? If I use this, so you can have many heaters on a 4-inch silicon wafer. As you can see, each reddish line that you can see, or greenish line you can see, are micro heaters. Okay, so thousands of micro heaters you can fabricate on 4-inch silicon wafer. So the idea is that, can you use this micro heater onto this flexible, integrate onto the flexible PCB? You can see a flexible PCB here, and then what you see here is a model of a trachea, that how we are going to insert the catheter. Right, this is a shape memory alloy integrated to the catheter. Shape memory alloy is at the end. You can see here, which is wire bonded between the micro heater structure, the orange one. You can see the shape memory alloy is in the end of this particular flexible PCB. The reason of using shape memory alloy is that it will remember the shape. Okay, when you heat it, it will shrink. When you cool it, it will come back to its original shape. So what will happen if you know the spring mechanism? If I have spring on two sides of flexible PCB, if I heat one side, it will bend, right? Because it will expand, and then cool it down, it will shrink back, or vice versa. So if I can maneuver the catheter in both the sides, right? Because I am inserting the catheter in the trachea. Trachea is generally D shape. Okay, when D shape, this particular line and this one is a flexible tissue, or it's a tissue, and this particular D, which is the circular one, right? It is the bone. So I only want to understand the elasticity of the side of the tissues, not really bone, right? So I can maneuver the catheter in both directions using the smart actuators. There are flow sensors or micro heaters. If I keep the temperature sensor, let's say at 37 degrees centigrade constant, okay, and I cover this entire catheter, like you can see here, right, is completely covered with a window opening as a micro heater. If the person breathes in and breathes out, there will be flow of air. Because of the flow of air, the temperature of the sensor would reduce, right? And based on the reduction in the temperature, I can understand that whether the trachea is inflamed or not. If at certain places the trachea is inflamed, right, then the temperature variation would be different. With that particular approach, trachea, I can see here, there's a trachea, it is stenosis. So we have deliberately create a stenosis mechanism. Stenosis is inflammation. Okay, you can tie the wire next to the shift trachea and it will become narrow. And what we do is, we have this instead of lung, we use a balloon, and then we insert the conflict catheter inside this shift trachea and understand how the temperature is changing when we apply different flow rate. So you can see here, right, we are able to see for the normal versus a stenosis tissues, you have a different change in the variation, right? It's a normal tissue, shift trachea, versus a stenosis one, right? So this is our first study. The second study consists of fabricating the force sensors and understanding it further. So this is one simple example that I have shown it to you. That people say that what's the use of a micro heater, right? It is just a micro heater. But if you use a micro heater, right, which is a micro temperature sensor in a catheter, it becomes an application. It becomes a catheter, and it becomes a biomedical tool, a biomedical umbrella of biomedical robotics, right? So this is where we are. We are working on another part of the study. Again, ethical clearance for using the trachea or the shift trachea, and Institute Biosafety approval to use the tissue. Now let us go to our next topic, which is on cardiac ablation. Yesterday I have touched a bit of it, but let me go into detail. Right, it's a smart catheter for cardiac ablation. When it's a smart catheter, understand that there is a sensor. Sensor remains as the heart of most of the systems that we develop in medical devices. Okay, let us understand the background and statistics. The image that you see right now, right, it is a heart-related disease are increasing day by day. We all know, right? Recent study shows that this disturbance occur in large proportion of the world. Right, there is a need for an accurate and affordable treatment. You can generally see that the heart pumps regularly, and because of which you will have this PQRS signal. Particularly QRS signal is very important. The signals you will see in a ECG, right, which is cardiogram, and then you will understand that if we this is how the generally heart pumps. But if there is a AFib, then heart starts pumping abnormally. AFib is a part of arrhythmia, and arrhythmia is a pumping of heart at its very higher rate. But in AFib, because of the abnormal electrical signals, right, there is a irregular heartbeats. You can see here QRS, and then there is a again irregular heartbeat. So you can see that why it is happening, right? It's a misfiring of signal. This is not how it should happen. Okay. So what is the way to treat this? Either you have to remodel the tissue, or you and what are the consequences? Sorry. So the consequences are that you see here in this particular image that the heart tissue gets deteriorated. The second thing is there can be a clot that can go somewhere, and it will cause a stroke. So the right way to treat is immediately is to give a right medications. However, in some cases the medication will not work, and that's why we use catheter ablation, or catheter. We insert the catheter, right, like this. What you see here from the groin area, the catheter is inserted all the way to the heart, and then the surgeon will identify where is the misfiring of the signal, right? So if you see, I'm sorry. Yeah, in this case, yeah, you see, there's a misfiring of signal, right? So the catheter will come all the way here, okay, and they will understand mapping of signal. Once the electrical mapping of signal is done, the surgeon will understand that where is the misfiring of signal, and the catheter is inserted, which is RF ablation catheter, into the body. So let us go to that particular slide here. So when the catheter is inserted to that particular part of the tissue which was misfiring, we apply a RF ablation. RF is a radio frequency. Ablation is heating. Okay, so when you heat the tissue at using RF frequency, it will burn. All right, burning is called ablation. You are using RF, so radio frequency. All right, so that's why it's called radio frequency ablation procedure. What you are using is a tube. It's called catheter. That's why the process is called RF ablation catheter. Okay, and now you want to know that if you apply a radio frequency, you need to touch that particular part of the tissue, right? It's very simple. When a surgeon touches the part of the tissue, he or she will be able to see the force, because if the force is higher, instead of burning that particular part of the heart, right, tissue of the heart, the other part will burn. Right? If the force is less, what will happen? Reoccurrence will happen. That means that the patient will again have the same episodes after the surgery is done. So the optimized amount of force is very important. And that means that you would have guessed that what we require? We require a force sensor. Right. So the force sensor that we design, you can see here, this is a catheter tip, and this tip is just very tiny. Okay, it is just for you to understand. I have just shown you the blown up diagram, and this is a force sensor that we have fabricated. Right, in the lab, we have also fabricated this tip, and we are performing experiments with pig's heart, right, to understand that how the force sensor values are coming onto the screen. But that is not a question. The current commercial ablation catheters also can show the force, which is called catheter contact tip force. All right, but none of this catheter can show or can give the haptic feedback. That means the surgeon will not be able to feel how much force he or she is applying. They will be able to see, but they will not be able to feel it. When you are able to feel the force, then the surgery would probably become better. That is the concept, and that is why we are working on a catheter that can also give a haptic feedback by designing our own force sensor, by designing our own tip, and using the catheter. And that's why we call it a smart catheter, because it will give a haptic feedback to the surgeon. Challenges: minimally invasive surgeries are challenging due to difficult indirect viewing of location, right? Although electrophysiologists can make out of the force feedback, I'm sorry about the spelling, to the handheld catheter while performing surgery, but it is a majorly depending on the operator. Then precisely detecting of force acting on your tip while performing surgery is very important. Accurate prediction of steam pops when you heat it, right? Because the tissue is also having water, right? So there will be steam pops. It's very important that you predict the steam pop, right? And then the X-ray transmurality. So what is transmurality is whether these are tissue. Suppose the thickness of tissue is this much, like my mobile phone, right? If I apply a force on one side or apply a heating on one side, whether the complete tissue is burned or not, that is a transmurality. That is another point, right? So need of R is that we had to design a haptic feedback to the existing catheter, right? And MEMS-based force sensor can improve the accuracy, sensitivity, and also have maybe possible to trace the location of the catheter. So aims and objective would be, there are 4 different objectives. Again, the final objective is to design a catheter for using it in live animals like pigs, right? To do that, we have to design MEMS-based force sensors integrated with catheter tip. Then we have to understand the performance of the fabricated force sensor using human heart tissues, design and development of a novel catheter integrated with MEMS-based force sensor using haptic feedback, and so on and so forth. A lot of objectives are there. What we have done till now is we have designed this catheter. Again, whatever I am showing is a research that is going out in my lab, and we believe that most of the things that I am telling you today, right, we are the first group to work on this kind of mechanisms. Okay, so you will not be able to get it from your books. It is more like application of your engineering and science into real life application. So this is a catheter. There is an ethanol wire, which I said is like a SMA. Right? You can just pull it, and ethanol is better than steel wires, and that's why generally use ethanol as a spine, while steel wire to maneuver the catheter. This is an actual force sensor. As you can see, the size of the sensor is extremely small, right? And then we are doing a lot of indentation and characterization techniques to understand the sensitivity values to characterize the force sensor to get the results. Right, these are some of the results at micronewton or millinewton of force. You can see it's very sensitive with about linear range of R-square value of 0.98. These are some of the optical profilometry to understand what is the depth profilometry of the structure that we create. Because if you see here, right, there's white thing is a through structure, and this 4 bridges are there onto which the catheter is there. On which the entire sensor is there. Okay. Again, ATAL clearance and IBSC approval. So let me go to another topic, right? And 2 more topics, and I'll stop. But very important, why I'm telling you many things rather than going into depth is so that you understand the broadness or broad things about different sensors, or the way you can use different sensors for different applications. Okay. So please ask me questions if you have any. Right, note down the questions while I am discussing, right, and we can discuss after the end of this particular lecture. So the next one topic that I want to discuss with you is on minimally invasive bioresorbable device to record ECOG signals for anti-epileptic drug screening. Now, let us understand what is ECOG. Like I said yesterday, that if you understand EEG, that is from the forehead, right? But if you understand ECOG, that is from the brain. All right. So the signals directly acquired from the brain is called electrocardiography, right? Where we can use for epilepsy. We can also use for stroke. Okay. So let us see. Epilepsy is one of the most common neurological disorders characterized by abnormal, excessive, and hypersynchronous activity of brain. You understand this? Epilepsy in a general term is called FIT. Right, there is no definitive epilepsy drug treatment. That means that a person suffering from epilepsy, the person is advised to take a certain drug. However, epilepsy, like I said, it can be granular epilepsy, it can be focal epilepsy, right? It can be focal to secondary epilepsy. Many things are there within the epilepsy domain as well. So it requires a mapping of brain surface to detect the source, followed by surgery. That is what intractable epilepsy. So intractable epilepsy is where the drugs are not effective. That means a surgeon has to open the skull of the patient, understand where is that abnormal, excessive, hypersynchronous activity, and remove that part of the brain. Surgery. Okay. So there is a treatment for intractable epilepsy. Now, conventional implantable devices for monitoring signals require surgical retrievalments. The conventional devices, they implant on the brain, right? They fuse the skull, wait that the episode occurs so that they know where is the signal generating. Open the skull again, remove the device, and perform the surgery. Okay, what we want to design is, can you place the chip right there, and it will dissolve after 4 or 5 days once the episode is there, and surgeon can see the episode. So we are using a bioresorbable material that can get dissolved in body fluids on pH and temperature. Different pH and different temperature will have different effect. We are working on such devices that can be implanted onto the brain. I'll show you some devices. Right, we can measure the electrocardiography. It is a 32 channel device. If you have recently seen the Elon Musk company, right, they developed this the implantable electrodes, right. More or less, we are working on a similar kind of activity, right, with a very limited funding, right. He has millions of dollars to invest in that. We are using with few legs, but the point is we are working towards designing sensors that can be finally implanted in human brain. It is having a tremendous amount of opportunity, because if you understand the Parkinson, right, where the person's hands cannot be controlled, the motor skills cannot be controlled, the person cannot also eat something. As you grow old, there is a chances of having Parkinson. So how to control this activity? These are motor skills, right? So if you implant the chip in the brain at that particular area, can you control the Parkinson? It's called deep brain stimulation, by the way. So we are designing a type of deep brain stimulation electrodes along with neurosurgeons. We are designing this implantable chip for epilepsy along with physiologists and neurosurgeons. Right? We are designing the flexible chip for stroke measurements along with the neuro oncologists or pathologists. So there are a lot of opportunities in this domain if somebody wants to work on. Okay, having said that, next is that there are no commercially available implantable bioresorbable sensors for continuous monitoring of vital biopotentials from animal model under various conditions. So you see, before you go to human, you can also understand that whether this model will work in animals, right? And how you get measured by designing a chip, right? Using the materials such as magnesium, zinc, tungsten, right? These are all metals. If you talk about semiconductors and single crystal silicon or silicon nanomaterial, nanoporous silicon, you have polysilicon, you have amorphous silicon, you have zinc oxide, you have this kind of semiconductors. But when you go for insulators, you have silicon dioxide, silicon nitride, magnesium oxide, right, polyanhydride. So the combination of these materials will make a bioresorbable chip that can be dissolved in a human CSF. Human CSF is cerebrospinal fluid. Now, what you see here is on the left side, you can see that there is a sensor to measure intracranial temperature and pressure. On the center, you will see that, so who does this thing, right? The first group that did was John Rogers. His group was the first one to work on the bioresorbable, as far as we understand. And they have done wonderful work here. You can see a mice, right, with a complete implant. They implanted this particular chip onto the mice brain, right? And then there's a head cap, so you can transmit the signal in real time. The next structure you can see here is that when you implant this chip, right, you can understand that if there is a normal signal versus epileptic episode. You can see here there is a seizure, right? There are a lot of spikes, slow wave, right? These are all characteristics of seizure or activity, abnormal activity, or you can say that it is creating a epilepsy. The third work that you see on the right side, excuse me, is a fabricated device from PCL substrate. It is inserted again on the rat's brain. Basal, when you load penicillin will also cause epilepsy. When you put a drop of penicillin there, it will create epilepsy. You can see the seizures, right? And after 6 minutes, you can see the seizures. That means that this device is able to identify the epileptic episode. We have done some initial study. I'll show it to you in the rat model. So this is our concept. One of the concept is to design a chip, right, with 3 different holes for drug delivery. And these are 32 channels that we have used for measuring or capturing the ECOG signals. These are recording electrodes, and these are contact electrodes. Okay, this one. Now, how to fabricate this device? So, like I said, I'm trying to put many things into this 2 hours, yesterday's and today's, but it is a more than 30 hours course that I teach to my students. Okay, so it will be difficult for you to comprehend some of the things. So please don't worry that you don't understand. It is a complete subject that one has to understand to come to this particular stage to understand everything in detail. So just understand the broad point of view that you can design a chip if you know microfabrication. You can design a chip that can be used for measuring ECOG. You can design a chip that can be used for understanding drug delivery or efficacy of the drugs. So you understand that there are 3 holes here, right? There are recording electrodes, and then we have 3 masks. all this structure is completely covered by silicon dioxide, which is an insulator. Only the recording electrodes are kept, windows are open, so that you can, there is a metal that can touch the brain of the rat, and you can measure the ECG signals. This is how we plan to do our experiments, right? We will implant the chip and will get the signals. I'll show you some of the things that we have done till now. But to give you some example that we have actually fabricated this device, you can simulate a lot of devices. The fabrication becomes difficult. You can only fabricate when you have a fab lab facility, right? Fortunately, we have the fab lab facility in the institute. I also have shown you some of the lab facilities that I have in my department. So these are how the recording electrodes looks like. You can see the gold, you can clearly see. The other part are also gold, but because it is covered by silicon dioxide, you can see that the color has changed. Because silicon dioxide is transparent, the light passes through it, the color won't change, right? And then these are the contact pads, right? So ATAL clearance to use the drug for rat epilepsy model, and of course there is a biosafety approval. So let me go to I don't know whether the time is permitting or not. So let me skip this thing, and if the time permits, I'll come back to this particular work, right? I'll just go to the next section here. Yeah. Not here also. Just excuse me for this one, because I don't want to show you too many things. It will be overwhelming. Let me go to the same thing which we are using for red brain implantation, right? This is the structure. Yeah. Okay. Microelectrodes, we'll design, we'll show you, and we go to the drive. Okay, yeah. Let me come to this particular another work of mine. Right. Again, when I say mine, is not mine really. Like I said, all the work is done by students. Right. So it is in vivo intraoperative probe integrating with MEMS-based sensor for improving glioma resections. Okay. Again, you are talking about MEMS-based sensors or advanced sensors or smart sensors. Why? Because this is very big problem in brain surgery, okay, brain cancer. So brain cancer can be divided into two main cancer. The one is glioblastoma and another one is meningioma. So around 2 lakh per year, right, cancer deaths, brain cancer deaths occurs. When someone has to operate the brain, when the skull is open and the dura is open, there is a cerebrospinal fluid. Okay, that will create an inequilibrium, and that's why the brain will shift. That means that a surgeon only has to open 4 centimeter diameter. He or she can only open 4 centimeter diameter of the bone, which is skull, and through that 4 centimeter they have to do the surgery. Okay. Now, where to reach? How they know that which part of the brain is causing cancer? Using MRI, right? fMRI. Now, once they look at that particular part, when they open it, right, when they remove the dura, there is a brain shift. So initially the cancer was at a particular place. When they open it, it has been shifted a bit. So brain shift is very important problem. Then they have to visualize tumor, right, within that 4 centimeter, whether there is a change in color, whether there is an angiogenesis. What is angiogenesis? Angiogenesis is creation of extra blood vessels, right, so to support brain, so to support the cancerous cells. Cancerous cells are a normal cells which have become notorious, right, to give you a very simple example. That means if you see a very notorious person, right, the use of energy is extra. And that's why the intake of the energy also requires more. That means a notorious child would eat more compared to a child who is calm, right? So you understand that cancer is like notorious. So it requires more energy, all right? And to require more energy, from where it can have more energy? From blood. Directly blood cannot give energy, but blood will diffuse the nutrition and oxygen to the cancerous cells. That's why there are more blood vessels when there is cancer compared to normal tissue. So that is called angiogenesis. The color would change, okay? There is a hemorrhage, right? There is a consistency of the tissues. So these are all things that a neurosurgeon is taught when to see or how to see a tumor and how to operate the tumor. Okay, it's very difficult. Let me go to the 26% of survival rate. Only 26%. It is found that more than 70% extent of tumor resection can be improved if it is a first year survival by around 26%. That means that if you by 1 year, if you can identify correctly, if you can remove the tumor correctly, the improvement is better. Impact of hospitalization is already we have discussed in many other problems. There is a difficulty with the out of pocket expenses, the facilities that are available, the limited number of neurosurgeons, clinicians. There is a radiological limitation. Not all the facilities would have a enough amount of fMRIs and other things. So there are difficulties, but there are challenges also. The challenges is that when a surgeon will look at the tumor, right, like I said, they have let me give an example. Okay, I hope all of you can see my mobile here, right? Don't worry about the tiger here, just see this camera, right? So let's say this is the cancer, this camera is a cancer. Okay, what neurosurgeon will do is he or she will remove this big part like this around the camera, including camera. Okay, why? To make sure that this camera which was cancer, right, completely comes out. But in doing that, they are also removing the normal part. They are removing the normal part. Now this normal part is connected with different body activities. Can be motor skills, can be visual, can be your other sensory parts, right? So we have to design an intraoperative probe so that you can only get this tumor and you can identify the tumor boundary compared to normal. Okay, so how close you can tell a neurosurgeon that there is a tumor, how can you delineate tumor boundary from normal, is a problem that we are addressing. This is a problem, this is a challenge in almost all kind of cancer. So that if I am working on brain cancer, you are open, you can work on different area of different cancer and develop a different kind of probe, right? This is a challenging problem, it's an open-ended problem. I would like that you start working on this domain, right, and start your own sensors and a probe. So let me give you some regions of the brain. There's a frontal cortex, this one, all right, parietal cortex somewhere here, temporal cortex here on the side, right, basal ganglia, I cannot show it, is inside, hippocampus, right, then there is a cerebellum, there's a thalamus, occipital cortex, the visualization that you see, it comes here, okay, the audio that you see, it comes here, all right. So lot of different parts of the brain does different activities. Now we want to try understand that what is the difference between white matter, gray matter, what is the different tissues, different part of the tissues. So you can see here we have taken a different sections of the tissues. Of course, when I say we is along with collaborators, you can there is a frontal gray matter, there is a frontal white matter, there is a corpus callosum, there is a cuidate, there is a thalamus, intercapsule, putamen, hippocampus, and lot of other things, right? So let us not worry about it. The point is, can we what if I measure resistivity of each part of this tissue? Will the resistivity will be different? Okay, to measure resistivity, what I want, just two sensors, right? If I place two sensors across the tissue and apply a voltage, either will be flow of current. Depending on flow of current, I would know what is the resistance of the tissue. I know that the length of the tissue, I know the area, so I can measure the resistivity, right? So this is very simple. Resistivity can I measure? But to measure resistivity, you have to design a system. You can see a complete system that we have designed. There is a microchip that is fabricated, which is integrated onto the system. And you can see here very clearly there is a tissue placed, right? Apply a voltage between two probes, top indenter and the bottom indenter, right? And you will be able to see the change in current, right? This is a simple circuit, right, that we use to measure the change in resistance or resistivity. You can see here different blocks of the brain. We have identified, we have taken the actual human brain tissues, three different subjects. Each subject we have taken different regions, like you can see here, FWM, FGM, CC, IC, putamen, CAU, thalamus, hippocampus, and then we have compared what's the resistivity for across each subject. We have also measured resistivity between the normal and glioblastoma. You can see very clearly here. We have measured the change in the mean and median. We have also understand not only the simple part of the tissue, but we have rotated. That means what is the, because tissue is anisotropic. If you remember yesterday's lecture, right? So across anterior how it will change, across superior how it will change, or medial how it will change. So superior, granular, different terms are there that are used. Don't worry about it. The point is that you can measure as resistivity of different part of the brain by using a simple sensor. isn't it? So the next part of the study would be to understand the viscoelastic models. We are working on this, so I'm not going into detail. However, we have fabricated a force sensor, which is another part of the study. And here, as you can see, there are four piezoresistors. You can see right over here, right, in this structure also, right? These are boron diffused onto silicon. If you know diffusion and ion implantation, which most of the electronic engineer would have studied in their course, right? There are doping techniques. You have a intrinsic silicon which is not doped. There's an extrinsic silicon which is N-type or P-type dope, either pentavalent impurities or trivalent impurities. How to dope that particular part of the silicon? Suppose I have N-type silicon, I open a window, right? I possess silicon dioxide, open a window so that I can only see silicon, and I want to diffuse only that particular part. What is the technique? How to diffuse it? If you have diffusion techniques, right? You know there is a predeposition and there is a drive-in. Predeposition step is around 400 degrees centigrade. Drive-in is at 1100 degrees centigrade. You have to use nitrogen plus oxygen to nitrogen along with oxygen to and there is a boron source. There is a three different type of diffusion: liquid diffusion, solid diffusion, gaseous diffusion. All these things should be very much clear when you study in your undergrad, right? It's a very simple thing, very basic things I am talking today, but extremely useful when you see in the terms of fabrication, right? If I know what is silicon, so you must have studied 4-inch silicon or 2-inch silicon. You have studied 100, 111, 110, different kind of crystal orientation. You may have studied how the P-type and N-type you can identify, right? You would have studied how silicon is fabricated using two different techniques, Sokralski technique or float zone technique. These are all under VLSI characterization or VLSI design, right? So you if you know these things, right, it will be very easy to come to this step where you want to diffuse a silicon wafer only in this structure. You can see here there's a green color, right? A light green color structures. We have diffused boron into these structures, and then there is a gold contact all the way forward. And this is an N-type silicon, and the boron is P-type. If it's a polysilicon, it will give us a piezoresistive effect. What is piezoresistor? Was it piezoelectric? I asked PhD students, right, when they apply for PhD interviews, they were not able to even identify what is piezoelectric and piezoresistive, which is very sad for me. But just to give you an example, or just to tell you definition, it's very simple. Piezoelectric, when you apply pressure, there is a change in voltage. Piezoresistive is when you apply pressure, change in resistance, right? That's it. Very simple. We're talking about piezoresistor here. So when you design a piezoresistor sensor, if I place a tissue on this piezoresistor sensor, what will happen? That if I apply a force, the sensor will bend. Why it will bend? Because there is a diaphragm. On the back side, there is a diaphragm. So depending on the stress that is created, the piezoresistor will change its resistance. Now the force that I apply and the force it reaches to the sensor would be different. Why? Because there is a tissue in between, right? So I can understand from that back calculation how to measure the elasticity of the tissue, or how to understand the stiffness of the tissue. That is the idea. The final idea that we are working on is to add the ultrasound sensors, to add the electrical sensors, and to design this probe. We have filed a patent for all the things I have shown you. To most of the problems or projects, we have filed a patent. Here there is a biochip at the end, and there's a biochip carrier, and then there's SMA actuator, so that you can maneuver the catheter inside that 4-inch area, right? And then you can measure different whether you can delineate whether there is cancer or whether it's normal, depending on the different properties of the tissue. Let me go to the last topic for today, and very interesting because I wanted to show it to you that you can design a transparent electrode array. If you have seen that we have shown you, or I have shown you the bioresorbable sensor, right, where you can see the chip recording electrodes. If you can design a sensor that can be implanted but is flexible in nature. Why flexibility is very important? Because you can then conformality will be better, because it will have a better sticking on the vein surface. So we are designing this particular sensor array, and actually I should say we have designed this flexible sensor array, and you can see a signal acquisition system. There is a conceptual interfacing unit where we want to implant this particular sensor onto rat's brain, right? Now, why to do that, and what is the use of this? We can see if there is a stroke versus normal tissue, and we can understand it in the GUI, what are the stroke regions versus what are the normal regions, right? Indirectly, if I place this thing on cancer also, I can know what are the cancerous region, because the tissue resistivity will be different. The ECOG signals coming from that particular part of the brain will be different compared to the normal part of the brain. So we are using a stroke model. There is a transition occlusion of the middle cerebral artery, right, which is here. If you press this artery for a long time, because of the flow, oxygen is stopped, there will be stroke. If there is a stroke, the property of the brain would be different compared to the that stroke area would be different compared to normal brain. So we have designed these flexible sensors. You can see here, right? There are some 32 recording electrodes at the tip of the sensor. Everything is flexible, right? And if you want to see the fabrication process, those who know can easily understand that we have taken a silicon wafer, we have sacrificial layer as a silicon dioxide, and you have coated a spin coater, which is a photoresist, and then you have done a mask 1 to form titanium gold patterning, silicon dioxide again, opening the window, and you have the sacrificial layer. So when sacrificial oxide will be etched, when it is etched, you can release this particular sensor. Again, it will be very difficult for a lot of you to comprehend because you have not understood the photolithography process in detail. But like I said, this is like a 30 hours of course that you need to take to understand what I am talking about when it comes to fabrication. Okay, don't worry about sensor. You right now understand that there is a sensor that we have fabricated. Now, if you have fabricated a sensor, what to do with it? So this is how it will look like. You can see a 4-inch silicon wafer or 3-inch silicon wafer on which you have many sensors here. Like I said, some are small in dimension, length is smaller, some are longer in length, right? Because depending on where you want to place it and how you want to take it out from the rat's brain, right? I'll show you now the actual study that we have done. This is an actual flexible sensor. We are implanted in the rat's brain, right? And you can see that the skull is placed back, right? And the chip is implanted here. This is used for taking out the contacts. Okay. Now you will say that, so what? You have done a surgery, you have placed the implantable sensors, you are measuring ECOG. So what? Right? Is a rat alive, or you are just showing us some photos, right? So the point is, after doing the surgery, you can see this video, and in this video, you will be able to see that there is a chip in the rat's brain here, right? And the rat is able to move, able to do all the actual activities that it is supposed to do. This is 1 day after surgery, okay? 1 day after surgery, right? It is healing, so that's why it's scratching, okay? It's healing, it's scratching. Now you can very clearly see, right? It's beautiful because that means that the surgery is okay. The implanted sensor is not causing any biotoxicity within 1 day. A rat is not dead, at least for 1 day, 2 days, 3 days. We want to make sure that it is alive for the lifetime until its life is there. And let me go to the last one, which is again, don't worry about the some of the red poops, but just see the that it is at 3rd day. You can see that healing is getting better, right? Healing is better, isn't it? And the chip is still intact. Chip is still intact. That is doing all normal activities. There is no change, right? So that means that the sensor that we have fabricated, we have implanted, can be now used for different kind of activities, starting with understanding the stroke, understanding epilepsy, using it for Parkinson, and so on and so forth. So this is what I wanted to cover in this particular module. I have many things to say, right? Many things to show. Like there are about 25 projects that we are working on, or maybe 20, not 25. So I can keep on talking and telling you a lot of things, but I want to also give you a chance to ask me questions, right? So I think I'll stop right now and would rather ask you to ask me a few questions so that it can be more interactive session. Thank you. I can talk about other topics if you like to me to talk, but for now I'll stop here and I'm free to take any questions if you have any, please. Thank you. Yeah, I can see one question from Krishna. That is that, can we reduce the size of the implanted sensors? Yes, of course. The size of the implanted sensor is actually, I have not shown it to you, but let me just, okay, since you have asked, let me show you this work as well. where the size of sensor is only 300 microns. Uh, I'll go to some microneedles. Yeah, here, right? So you can see this particular fabricated microneedle, the size is only 150 microns, the width. Okay, this width is only 150 microns. This is longer, but this width is extremely small. This can be used to implant in the red to understand different signals from the cortical columns. So you can see these are different dimensions, and then we have actually fabricated microneedles of different dimensions. Another topic of utmost interest for neuroscientists, right? There are some of the microneedles integrated with recording electrodes we have fabricated. And then there is a PCB, we do wire bonding, and then we actually implant it in the rat's brain. So yes, we can reduce the size of the implantable sensors. Second is Somya is asking, design and fabrication of sensors you have shown can be done in your labs. These are sensors from my lab only. All the things that I have shown is what we fabricated at IISc, okay, in my lab. And you will see publications coming out soon. We have filed patents on the same. So I'm sorry if I was not clear. All the things, when I take a references, I'll say that it is from Rogers Group or something else. Sorry, so yeah, so all the sensors that I am referring, I'll always say that this is done by some group. When I'm not referring it, that means it is done in our group, at my lab, in my department, in my institute. Okay, so right from modeling to simulation to fabrication to testing, everything is done. Yes, when it comes to surgery, we have taken help of neurosurgeon at Niemans who has done the surgery. What is the software using for fabrication of sensor? Oh, we don't use any software. I'm sorry, I don't understand the question, Venkatesh. But let me give you an example of Covento, where Covento gives you a bit of understanding of the fabrication details. There's a process flow that you need to understand, and then you have to come here or come to the lab where you actually start understanding the fabrication by using the equipment. There is a simulation software which is COMSOL Multiphysics that can be used to simulate different sensors. But I don't think you can learn fabrication of sensors just by using software. It is more like you have to get your hand dirty by working in the laboratory. Of course, the laboratory clean, so your hand will not be really dirty. But before going to fabrication, is there any hardware testing is possible? I still don't get it, Venkatesh. Can you ask me maybe through the uh, forum, because what exactly you want to, which kind of hardware testing you're talking about? You want to test your chip if you have fabricated a chip, or you are telling that you want to test your design? If you want to test your design, you can always use simulation, COMSOL simulation. Like I said, you will understand more or less how the design would come out and how the performance would be there for that particular sensor. When you fabricate it, always understand that there will be a difference in the simulation result versus fabrication because of the process flow and recipe that you use in fabrication. So there will be 10% tolerance to 15% tolerance based on what kind of fabrication facility you use. Yeah, but we have to have a proper mechanism, Krishna, to have this. You can come here and learn the things, or group of you can come here and learn the things. There can be a workshop that we can conduct, but I need to go through a proper forum, right? Taking permissions, but yeah, there is a possibility. We can organize a kind of a joint workshop between IISc and your place, my department and your place, and a part of workshop you can come here and we can do that. We can discuss offline. Yeah, I would be happy if you make my life difficult, right? Not easy. So please ask me questions. You should have. I believe that you should have a lot of questions. Any question that comes to your mind, you can ask. Okay, feel free. I'll try to reply as much as I know. A lot of things I don't know, so I'm not able to reply. But things that you like, it may be out of your curiosity, you are free to ask. Yeah. Yeah, I think if you don't have any question, then I should let you go and you can let me go. But if you have any questions, I thought that yesterday I took a lecture, right, 1 hour. So you'd ask me a lot of questions. You would have prepared a lot of questions. No? Okay. So yeah. So Krishnavani, if any other questions are there, I can take it. Otherwise, I think we are done for now.
Sir, one question from my side.
Sure, please.
Sir, you have explained about lot of sensors. Can you show any biovariable devices? Do you have any biovariable devices right now in your labs? Sir, you're on mute. Please unmute yourself.
Yeah, just I'll show you a EEG band. Just give me 1 second. I need to bring it. So I'll ask my student to bring it to my office, and I'll show it to you how it works also. Just give me a second.
Okay, sir.
Student, he will bring it. So before he brings it, let me just show it to you what we are going to discuss, so that it becomes easier, right? Let me show it to you that particular project. Okay. So this is a screening technique, right, to understand whether a neonate, a newborn baby, can hear or not. Okay, and there are two ways to understand it. One is to understand through auditory evoked potentials, or AEP. The technique is called ABR or BERA, and the way it is done is that when a neonate is born, stimulus is given right through the ear, and the ABR is recorded. And if the ABR is coming correctly, which is within first 10 milliseconds, right, the baby is declared as it can hear, he or she can hear. Okay. Now the problem with the this current technique is that the system itself is about 14 leg, 1/4, and a lot of tertiary clinics they have it, but secondary and primary clinic does not have it. So what happens is the babies that are born in primary healthcare centers or even in the secondary healthcare centers or nearby, in the area where there are no tertiary clinics, they don't go through this BERA. That means that parents would not know whether a baby can hear until the baby is about 2-3 years old. That means that the cognitive ability will decline or will get affected if the baby cannot hear, because hearing impairs the speech, right, and other abilities. So early recognition of hearing of a neonate is very important. But if we don't have a system that can measure, it's very difficult. So the way to understand this, yeah. I'll be back in 5 minutes. Okay, thanks. So the way to understand this particular stuff is by designing a band that can be used, right, for understanding whether a baby can hear or not at a time of birth. But it should be cheaper. It should be affordable rather than cheaper, we can say, right? So and we want to just use it as screening module. Okay, so there are two things. Again, OAE is just outer ear, it will see. ABR is good, it is like for 14 leg, 12 leg, 15 leg. So what we want to understand is that not only the so how the auditory cortex works, okay, is from the outer ear to the cochlea. Through cochlea it reaches to auditory thalamus, and that's it. So people can only look at this particular structure, which is your first 10 milliseconds, first 100 milliseconds. Now, if for ABR it is just 10 milliseconds and you are done. We are proposing to understand a further auditory circuit by looking not from just ear to auditory thalamus, but all the way from ear to auditory cortex. That means the entire pathway we want to study. That means entire auditory circuit is working or not. That is one. Second is to design a band that can be used on a small baby, right, at some point of time, so that it will show baby can hear green light, baby cannot hear red light, the reason is inconclusive, orange light. That's it. So to do that, what we can do, we have to have a EEG electrodes, right, like this. And then there is a electronic module, and then there is a signal, that is the EEG signal that you acquire should go to your electronic module, right? So these are the things we are planning. I'm not going into detail, rather than I like to show you the system that we have developed for the young adults for now, and then I'll take it further. So if you can see what I'm showing it to you, which is I'm holding right now in my hand, right? Let me just make it bigger so I can also see myself. Yeah. So these are all the wires. Don't worry about the wires that are coming out. There are EEG electrodes. You can see here 1, 2, 3. There are EEG electrodes, right? A person has to wear this thing, right? Like by putting these electrodes like this, and they have to wear it like this. You can see here, right? I'm able to wear it like here, okay? And then there is a ear clip here. So ear clip, one is for reference, like this, it goes, and one is for ground. Right, let me just put it correctly. There should be a person who should help me. Right, okay. So reference, ground, and these are two stimulus, auditory stimulus, headphone or earphone. That's it. Now, if of course I have to place it properly. Now everything will be done here in through this. Okay, and you can record on a signal on a system. Now, if the baby can hear or somebody can hear, it will be like green, not here red or orange. So this is a system that we have developed. Like I said, it's very easy to use it, right? I have used my own. The idea is that it should be used by a primary healthcare worker or a ASHA worker, right? So this is very simple example of a wearable, right? Yes, we are also making a band that you can use like a watch, right, and can be used to measure the different things. They got a proposal from BIREC approved to develop a watch for measuring continuous glucose. So we are doing that as well. Yeah, but for now, I think that's what I have to show it to you, and what I have shown it to you. So, but if you have more questions, please ask me.
Thank you, sir. Nice explanation here.
Yeah, I think I have one more question. Let me take that question. Venkatesh is asking that how invasive kind of sensors will be tested. Yeah. So invasive kind of sensor, I have shown it to you the rat. No, first you have to go for the animal model, and then only you can go for human model. So initially you have to implant the sensor on the animal model. Can be rat's brain, can be monkey, can be rabbit. Once the signals are correct, when you prove the technology and the efficacy of the technology, then you are allowed to go for humans. So there is a way to reach to that particular modules. Invasive kind of sensors, like I said, we have implanted, and then there is a signal conditioning unit that can be attached to these implantable sensors to measure in real time. That's how it is measured, Venkatesh. Yeah, any more questions? Okay, I think there are no more questions. So thanks once again, all of you, right, for giving me this opportunity, for having me here yesterday also, today also, hearing me for 2 hours. Right, it's long 2 hours, but there are many things in this particular area that one, if one is interested, can work on. Right, an exciting area, lot of opportunities, not only from funding point of view, research point of view, but there is a translational opportunities. At some point of time, if you save even one human life, that is worth you doing research. So that's what I believe. So thank you once again.
Thank you very much, sir. You highlighted the participants about the sensors used in medical applications and in clinical applications, but it requires good command in anatomy and physiology of both cardiovascular system and nervous system, sir. You have explained in a very nice way. Thank you so much for accepting our invitation, sir. It's a lot.
Thank you very much. See you then. Bye.
Sir, 1 minute.
Sir, 1 minute. We
Oh,
have
is
a
it?
screenshot with all our participants.
Is it okay?
Enable
My
the-
hair are messed up, but it's okay.
all the participants kindly enable
Done? I cannot hear, sorry.
We are done.
Then, sir, thank you so much.
Okay, all right. I think Sajid is asking my email ID, so I think Krishna has it. You can take it from her. Sajid.
Yes,
Yeah.
sir.
Okay. Thanks. Bye.
Bye, sir. Bye.